Hello, this is Nicholas, and I wanted to do some kind of intriguing integrals since we're doing integrals now and we'll really just use subs. So all of these integrals are going to be solvable using just u substitution and kind of some clever manipulation of your mind. So follow along with me, if I give you one and you want to try it out before I do it, pause it and give it a shot. So first one I'm going to do is the integral of secant squared x over secant x plus tangent x to the 9/2 dx. Now what do I want to do? When I look at this, what kind of pops out at me is the bottom part, right? This part right here. I want to just let that, I think. I'm going to let that be t instead of u, because no one cares about you. So, in other words, I'm going to let secant x plus tan x be equal to t. And now, hopefully you can see that if I take secant x minus tangent x, that's going to be 1 over t, because when I multiply this and this together, I get 1, and t times 1 over t will do that. This implies that secant x is equal to, and I'm doing all this right because I want to find what secant x is, because I have to substitute it in there. So, let me maybe show some more of my work. So secant x plus tan x, and then secant x minus tan x. I'm going to add those together. Those go away. Oh, and this is t, and this is 1 over t. So 2 secant x is equal to t plus 1 over t. So secant x is t plus 1 over t over 2. Now, I know that dt is differentiating this derivative of secant is secant x tan x plus secant squared x. Oh, look at that. Dx. So dt. Oh, yeah, that's actually really cool right there. That's secant x times tan x plus secant x dx. But this is just t. So in other words, dt is what am I doing? Is a t secant x dx. Yeah, that's gonna work out kind of nicely. And so finally, dx is a dt upon t secant x. Okay, now I get, what do I get? I get the integral. Now I'm going to have secant x times a dx over t to the 9/2 times t. Yeah. See, because I See, the secant squared x, it's a secant x. When I put this dx in here, one of these secants is gonna, see, we have a secant on the bottom, canceling with one of these secants on the top, leaving just a secant on the top. And we put in dt and we get that. Yeah, should be pretty intuitive there. So now we get some kind of clever manipulation here that I'm going to have to do. Well, not really that clever. Now secant x, if we remember from here, so we get 1/2, and put the 1/2 out front, integral of t plus 1 over t dt now. Everything's in terms of t. And t to the 9/2 times t is t to the 11/2. Now this is just power rule, right? This is exactly just power rule. So, I mean, I guess I'll follow it through. 1/2 integral t to the 1 over t to the 11/2 is t to the -9/2 plus t to the -13/2, and we integrate that and we get yada yada. In other words, I know you could do that. And then remember to just plug back in. You know, we don't care what t is, we care about what we care about in terms of x. We want it in terms of x here. So now, kind of a cool one. It might look kind of nasty at first, but let's work through it. So, integral x plus 1 to the third times x minus 1 over x squared plus 1 squared, how about this, times the square root of x to the 4th plus x squared plus 1 dx. Dx, there you go. So, what do I want to do? What do I want to do? I think what I want to do, I think what I want to do is, I know if I split this top part, this numerator, into x plus 1 squared times x plus 1 times x minus 1, I know that this is just the factorization of the difference of squares. And then from there I might have to divide by some power of x, but in other words, I would have an x squared minus 1 here and an x squared plus 1 here. So I could possibly use a u sub there, and I think that's where I want to go. So I'm going to make this the integral of x plus 1 squared times x squared minus 1 over x squared plus 1 squared times the square root of x to the 4th plus x squared plus 1 dx. Now, oh yes, okay. What I'm gonna do is I'm gonna multiply by what? I think first what I'm gonna do is just expand this first one out because it's small enough that I don't think it would make much of a difference. It's not a big, huge expansion or anything. So x squared plus 1 plus 2x times x squared minus 1 over x squared plus 1 squared times the square root of x to the 4th plus x squared plus 1 dx. Now, I think I see it. Now, I want to divide everything by x cubed. In other words, maybe, oh, that's a big eraser, wow. Okay, so I'm not going to use that. I don't want everything to go away, but imagine if I was to divide both the numerator and the denominator by x cubed. In other words, multiply by 1 in the form of 1 over x cubed over 1 over x cubed, and then now we have the dx out here. Now this might look like it might be making it worse, but there's kind of a lesson to be learned here. So now I get integral x plus x squared plus x plus 1 over x plus 2 times 1 over 1 minus x squared over x plus 1 over x squared times the square root of x squared plus 1 over x squared plus 1 dx. It doesn't look like I've messed up anywhere there. I just want to make sure here. Well, yeah. Yeah, okay. Okay. Now, why did I do that? Because now look, I get the integral of x plus 1 over x plus 2 times 1 minus 1 over x squared times x plus 1 over x squared times x plus 1 over x squared minus 1. Or, yeah, minus 1, yeah. In other words, I completed the square here. And you can follow it out and see, you'll get the answer. But now look at. If you differentiate x plus 1 over x, you get 1 minus 1 over x squared. So in other words, it would be a very good idea to let u be equal to x plus 1 over x, because then du is 1 over 1 minus x squared dx, and from that we get the integral t plus, or u, I used t in the last step, u plus 2 over yeah, u plus 2, and then this right here is du, so there's our du, and then we get a u squared square root u squared minus 1. And now I think what I want to do from here is I think I'm going to use another substitution. In other words, I'm going to see x is u is in terms of x. I think I'm going to introduce a new variable t that is in terms of u, and then later I'm going to rewrite t in terms of u and then u in terms of x. I'm going to basically undo two substitutions. So I think I'm going to because I don't like this. I don't like this here. So I'm going to let t squared, because if I have it t squared instead of just t, then the square root of t squared will just give me t, which is a lot nicer. So then that t squared is equal to u squared minus 1. So what? That implies that t dt is equal to u du. You'd really have 2's here, but they cancel out. So now t dt is equal to u du. That's kind of cool to say. So now we get integral well, we get 1 over 1 over well, this u squared becomes t squared plus 1. Oh, and that's nice. That's arctan. 1 plus t squared dt plus a 2 times the integral of 1 over u squared, I'm sorry, t squared plus 1 to the 3/2 dt. Now, from here, I think I'm gonna have to make another substitution. I think I'm gonna have to do 3 substitutions here. Did what I do there make sense? It makes sense to me. So okay. I think I'm gonna let what do I want to do? I'm gonna let t, and this might look suspicious here, but in other words, look at this here. 1 plus t squared. If I let t be equal to the tangent of theta, so that means that dt is equal to secant squared theta d theta. D theta. So now, in other words, we know, I'm only doing this for this second integral, by the way. This is just a arctan t. But now this one, I get plus 2 times the integral of 1 over 1 plus tangent squared theta, secant squared theta to the 3/2, which is secant cubed theta, times dt, which is secant squared theta d theta. So that cancels, leaving just a secant theta on the bottom, which leaves us with just 2 times the integral of of a cosine theta here, which is a sine theta. So we get arctan t plus 2 sine theta plus c. Now, so this is, if t is, that's really t over 1. So draw a little triangle here. This is theta, so the tangent of theta is t over 1. That makes this length 1 plus t squared. So the sine of theta is t over 1 plus t squared. So we get arctan t plus 2t over the square root of 1 plus t squared plus c, which is, oh boy, that's arctan of u squared minus 1. I didn't know what I was getting myself into, plus 2u squared minus 2 after you FOIL that out. What, it was over 1 plus t squared? 1 plus t squared is just u squared, so square root of u squared is u. Okay, and now we're getting there. Plus c, which is equal to, we should be almost done. What did I let u be? I really hope I wrote it down because I'm gonna forget. Oh, I let it be this. Okay, so arctan of x plus 1 over x squared minus 1 plus 2 times x plus 1 over x squared minus 2 over x plus 1 over x plus c. There it is. There is our answer. That one was cool, wasn't it? I mean, that one wasn't that. It wasn't crazy. Okay. Now, let's do one that kind of follows an unorthodox approach using complex numbers. Let's do the integral of cosine of 3 times the natural log of x dx. And now realize that it wouldn't make much sense. You know, you might be tempted at first to just let u be a 3 ln x because that's the input of your cosine. But realize that you don't have any factor of the derivative of the natural log of x. In other words, we would want an x on the denominator somewhere for that to work. Because if you were to let u be 3 ln x, then you'd have a du that would be 3 over x, and you'd end up getting a cosine of x over x, which would not work out so well. Here, let's do it. I kind of want to illustrate it. So let's let u be 3 ln x. Then we get that's equal to the integral of cosine of u. Oh, and then by the way, that means that du is 3 over x. So dx. So oh, oopsies. Yeah, I think this should work actually. So now that means dx is equal to x over 3. Oh, but then we need integration by parts. Oh, no, this wouldn't even work either way. Yeah, never mind. But so let's keep going. Dx is x over 3 du, so x over 3 du. So now, if we wanted to write x in terms of u, we know that u is equal to 3 ln x, which means that u over 3 e to the u over 3 is equal to x. Now we have, oh boy, so now we have cosine of u, oh, and I could put the 1/3 out here, times e to the u over 3 du, and you would still need integration by parts. So what we're going to do is we're going to go complex. So remember, for complex numbers, for a complex number z, cosine of z turns out to be e to the I z plus, that's for sine, plus e to the negative I z over 2, and sine of z turns out to be e to the I z minus e to the negative I z all over 2. And this follows from the fact that e to the I theta is equal to the cosine of theta plus I times the sine of theta, and e to the negative I theta, in other words, we're plugging in negative theta in for theta, is cosine of negative theta, which is just cosine theta because cosine is even, plus I times sine of negative theta. Sine of negative theta is the negative of the sine of theta, so we get minus I sine theta. Now for cosine in this particular, well, if I was to find this formula, in other words, write what I want in terms of cosine, I would add these two together. I would get e to the I theta plus e to the negative I theta is equal to 2 cosine theta, because those cancel, and then you'd divide by 2, and then that would give you your answer. Oh, not your answer, but in other words, that's where those formulas come from. I just kind of wanted to show that. So let me, not really that interesting in what we're doing. Oh, my line. Okay, so what this means is that, so cosine of 3 ln x dx. Well, first of all, cosine of 3 ln x is equal to 1/2 e to the 3I log ln x plus e to the negative 3I ln x, which is just one and the same as 1/2 times x to the 3I plus x to the negative 3I. And all I did there was I made this e to the natural log of x to the 3I. E to the natural log of x is just x, so we get x to the 3I. So it follows that this integral is equal to 1/2 x to the 3I plus x to the negative 3I dx. Now this might look strange to you at first, but this is just 1/2 times x to the 3I plus 1 over 3I plus 1 plus x to the negative 3I plus 1 over negative 3I plus 1 parentheses plus c And some simplification needs to be done here. But in other words, if you don't believe me that the power rule holds true for complex numbers, think about it some and do some examples and see what you get. Okay. Now, that equals doing some algebra. X times, parentheses, 1 minus 3i times x to the 3i plus 1 plus 3i times x to the negative 3i over 20 plus c. In other words, getting the i's out of the denominator and doing some algebra there. So that gives me x times x plus, or x to the 3i plus x to the negative 3i minus 3i times x to the 3i minus x to the negative 3i, again all over 20, and still plus c, which is x over 10 times cosine of 3 ln x plus 3 sine 3 ln x plus c. Ta-da! There it is. So the point of me giving that integral was just to show that you can still use complex number techniques in order to get real solutions, which is pretty cool actually. Now let's do let's do, I wrote some down and I'm trying to find them. Oh, let's do this one. Integral of 1 over x to the 7th plus x dx. Now, you might be tempted to go on like this, and these are all valid steps, by the way, but they don't really lead anywhere. You might make this 1 times x plus x to the 6th plus 1 dx. And I really don't know what you do from there, actually. But in other words, you might be tempted to factor out this x here because it's a common factor. But let me show you something. This is really kind of cool. What if I made this 1 over x to the 7th times 1 plus x to the negative 6th dx? In other words, I factored out the bigger power. Then I would get the integral x to the negative 7 for 1 plus x to the negative 6 dx. But now notice, this here, you differentiate this, you get negative 6x to the negative 7. So in other words, we can use a u sub here, right? We can let u be equal to 1 plus x to the negative 6, which implies that du is equal to negative 6x to the negative 7. So we get the integral negative 1/6, the integral of du over u. See, I did some stuff in my head there, but normally when you have this factor out here, what you can do is just reciprocate it and then put it outside. Because you're going to end up, this should have been a dx here, because you're going to end up solving for dx. And so you're going to end up reciprocating this -6 to a -1/6. So just kind of a trick you can do in your head. And now this is really simple, right? This is -1/6 ln absolute value. I didn't actually need absolute values. I could just do parentheses of 1 plus x to the -6 plus c. Ta-da! And I didn't need absolute value because this is always positive. Exponentiation's never negative in the real numbers. Okay, that one's kind of cool. And actually, in general, if you have the integral 1 over x to the n plus x dx, the pattern is still the same. In other words, your answer ends up being -1 over n minus 1 times the natural log parentheses 1 plus x to the -n minus 1 plus c. Just kind of cool. Okay. And by the way, as I'm doing these, follow along if you'd like. So integral 1, and this will probably be my last one, 1 over x times 1 plus x to the 119th power dx. Try and do this one on your own. It's basically what I just gave you. So try that one on your own. Okay. Maybe try this one. If I remember it right, sine of 2 theta over square root tan theta d theta. If I remember right. This becomes integral 2 sine theta cosine theta over tan theta to the 1/2 d theta, which becomes integral 2 sine theta over square root tan theta times cosine theta cosine squared theta over cosine theta d theta, which is equal to the integral of 2 sine theta secant let's do this. I can make square root tan theta secant squared theta secant theta d theta. Do it like that. Why did I do that? Why did I? Because tan theta, when you differentiate it, you get secant squared theta. So in other words, if I let u be equal to tan theta, du is equal to secant squared theta d theta. So I want this secant squared theta on the top. I want that on the top. So maybe what I can do instead is at this particular step 2 sine theta, I can make that, maybe I'm doing the wrong one. I think I'm probably doing the wrong one. Let's do a different one because I don't really remember it. I think I wrote down the problem wrong. I think there should have been something else in there. Let's do integral, this will be the last one, 1 plus sine 2 theta d theta. This is the integral square root 1 plus 2 sine theta cosine theta d theta. Now at this particular point, you might be saying to yourself, I'm not really sure what to do, but remember this. We want this square root to go away. It's not nice. I know that sine squared theta plus cosine squared theta is equal to 1. So I get the integral of sine squared theta plus 2 sine theta cosine theta plus cosine squared theta, oh, that's a very bad square root, d theta, which is the integral of square root sine theta plus cosine theta squared d theta, which the square root and the square go away. So now we just have the integral of the sine of theta plus the cosine of theta, which becomes sine theta minus cosine theta plus c. That's it. And we're done.